In this video, we're going to see how to do some calculations using these resonant modes. It can help us understand a little bit more about how instruments work. So just recall that these are called resonant modes. These are the resonant modes a string or any other thing that's fixed at both ends can vibrate at. Okay, so first question. A string that is fixed at both ends, and it's 10 meters long, has a standing wave pattern that has 4 loops over a distance of 10 meters. So 4 loops, if we sort of divide up the string into quarters, 1 loop, 2 loop, 3 loop, 4 loop. That's what I mean by loops. It's sort of these open areas of vibration. So this is 10 meters long. There we go. So there's the standing wave pattern. We know it's going to vibrate something like that. We know that these little spots here in between are called the nodes. So we'll mark those with N. And this has 3 nodes. The areas where it's vibrating the most between the nodes, we actually call those antinodes. So antinodes are the green ones there, because they're the opposite of the nodes. They vibrate the most. It's asking us here now what the wavelength of this wave is. So remember, a wavelength is 1 cycle. And if we look, 1 cycle of this wave sort of seems to follow, just get out of color here. 1 cycle is like an up, down, up, back to the starting point. So 1 cycle looks like that. If the whole wave is 10 meters long, or the whole string is 10 meters long, how long is one of those waves? In this case, it looks like it's half the length of the string, in which case it is. So the wavelength in this case is just 5 meters, half the length of the string. Pretty straightforward. Next, if the speed of the wave is 250 meters per second, what is the frequency produced? So remember, we create these standing waves by a wave that's moving along this way and a wave that's moving along this way, interfering with each other, creating this pattern. So if each of those waves is moving at a speed of 250 meters per second, what is the frequency produced? So in this case, we have this handy equation for wave speed, where it's v equals the frequency times the lambda, where lambda is the wavelength, right? Well, we know, based on what we did above, that the wavelength is 5 meters, and the speed is given in the question as 250. So if we want to find the frequency of the wave, it's just going to be the speed over the wavelength, which we know both of. So speed is 250 meters per second. The wavelength is 5 meters. So if we just divide that, we get 50. And if you look at the units, those cancel out, and we're just left with per seconds. And really, it doesn't look like it's there, but frequency is always in cycles per second, right? Cycles per second. It's like things per second, so we don't really have a unit for that. We can think of it as like down here, this is 5 meters per cycle. So then the cycle would come, in that case, the units make more sense, 5 meters per cycle. And in which case the cycles comes to the top and gives us that, which is the equivalent of 50 hertz. There you go. So just by knowing the length of the string and the wave pattern that is going to sort of happen on the standing wave that's going to appear on it, and if we know the speed, we can calculate the frequency. So 50 hertz, that's a very low frequency, and it makes sense because it's a very long string. So in this second question, we have a column that's opened at one end, an air column that's opened at one end. So if we want to draw that, we can draw it sort of like that. And remember, the closed end acts like a fixed node, and the open end acts as a open point, right, where it's going to vibrate the most. So if this is the case, we know the length is 1.2 meters, right? We know the fundamental is the lowest frequency it can play, so sort of like the simplest wave that can play, and we know that's going to look like this with no nodes at all. So what is the wavelength of the fundamental? And we can think about it. So this piece is 1.2. How much of the wavelength is shown here? Well, remember, if we were to continue this, I'm going to continue with a dotted line. Oh, and the what do we call it? The equilibrium point is along this line, right? If we were to continue this pattern along, sort of as a dotted line here, we would go down, up, and down. So that's what the whole wavelength would look like. The whole wavelength is not inside the instrument, it's beyond the instrument. But basically that's what the whole wavelength would look like. So what's inside the wave, inside the instrument is 1/4 of a wavelength, right? Because the rest of it is, only 1/4 is shown. So if that's the case, the wavelength of the fundamental, the wavelength of this note, is just going to be 4 times this 1.2 meters, which gives us, 4.8 meters. So that's the wavelength that this instrument would play. And if we wanted to do the frequency of this, let's just erase that. If we wanted to do the frequency of this, we know that so frequency is equal to, our speed, our wave speed over our wavelength, right? Do we know the wave speed in this case? Well, luckily we know that this is happening in air. And when we have speed moving through the air, we actually have a nice relation that gives us a hint or an approximation of the speed of sound through the air. Because the hint to that as well is we know the temperature of the air, 20 degrees Celsius. So if you know the temperature of the air, you can calculate the wave speed, and you know the wavelength because we calculated it here. So I'm going to actually leave that as an exercise for you. The answer is here, 71 hertz. So if you calculate that, see if you get the correct answer. So pause the video here, try it yourself. Okay, hopefully you actually tried that, because we're just going to move on to the next question here. It next asks us to calculate the frequency of the first overtone. So if we have the same instrument with the same open at one end and the same 1.2 meter length, we know one end is fixed and one end is free. We know that. The fundamental is sort of the simplest version of that, right? Where there's no nodes between it. But the first overtone does have a node between it, right? Because you're increasing the frequency by decreasing the wavelength, and you're going to have one node between it. Let me draw the equilibrium point as well. So the one node created sort of ends up looking like that, right? That's our pattern for the first overtone when the one end is open. If this is the case, how much of the wavelength is in there? We can sort of see this if we continue it outside. We see that the wavelength finishes there. So this is 3/4 of a wavelength. So if we wanted to know what the whole wavelength was, there's a few ways to do this. It's up to how it works for your brain. But for me, I see that I can divide 1.2 into thirds, right? So 1/3 of this length, if we were to divide into thirds, is going to be 1.2 divided by 3 is 0.4. And there's an extra 0.4 at the end, 0.4, that's going to complete that wave. So the whole wavelength is going to be 1.6 meters, just a little bit longer than that too. It's actually asking us this question for the frequency of the first overtone, and you can calculate that in the same way that we calculate the frequency of the fundamentals. So I'll leave that again as an exercise for you. Pause the video here, give it a shot. Lastly, we have a wind chime. The wind chime is 45 centimeters long. And a wind chime, it's like just a tube, right? It's a tube that's supported in some way. We can usually assume a wind chime is like a tube that's open at both ends. So it can vibrate, and both ends can sort of vibrate back and forth, right? Both ends of this tube can vibrate back and forth. And in order to do this, it's essentially like we have two open ends, right? Two ends that are free to move. If that's the case, in order to create a standing wave inside, we're going to have a wave that looks like this. This is the simplest wave we can make. We can't just connect these straight across, because then no wave would be made, because that would just mean the pressure is equal throughout. We don't actually have any wave being formed. So here we have, this is sort of the simplest wave we can create. And the length of it is 45 centimeters. We want to find the pitch of the fundamental, the frequency of the fundamental, if it's 25 degrees Celsius outside. So I'm going to help you with the first part. How could we find the wavelength? Because we know, to find the frequency, we know, as per the previous question, what was it? Frequency was speed over wavelength. Speed over wavelength. I think you know how to calculate the speed if we know the temperature outside, right? Just use that formula to calculate the speed of sound in air. But we need to know the wavelength. the wavelength. And if you look here, how much of the wavelength is shown? I'm going to show the equilibrium point here. I'm going to extend it a little bit. And if we were to continue this like this, on the top and on the bottom, how much of the wavelength is shown? Well, if you sort of divide up the wave into 4 pieces, 2 of those 4 pieces are shown in the middle. So this essentially is 1/2 of the wavelength, right? So if that's 1/2 of the wavelength is just going to be 2 times 45, which is 90 centimeters. All right, so that's the wavelength in this case when there's 2 free ends. So what you can do is you can calculate the frequency yourself, and it should end up being this 384 hertz. Okay, I'm going to leave that as an exercise for you. So please try that, and there you go.